In this video, we'll talk about the first and second derivative tests for identifying local extreme values. We begin with a question. How do you identify if a critical point belongs to a local maximum value or a local minimum value? There are two different tests that can help you determine if a critical point belongs to a local maximum or a local minimum. These tests rely on the first derivative or the second derivative, and as a result they're called the first derivative test and the second derivative test. Let's start with the first derivative test. The first derivative test is based on the increasing-decreasing function theorem and looks at the sign of the derivative function. So suppose that f is continuous at the critical point c. If f prime at x changes from positive to negative at c, then f has a local maximum value at c. If f prime at x changes from negative to positive at c, then f has a local minimum value at c. If f prime at x does not change sign at c, then f does not have a local minimum or a local maximum there. This test is just based on the relationship that the first derivative has with the increasing or decreasing behavior of the function. So, for example, if f prime of x changes from positive to negative, then that means that f changes from increasing to decreasing. When f prime is positive, then the function is increasing, and when f prime is negative, then the function is decreasing. So that means that you have some picture like this first one. Your function is increasing and then decreasing. The only way that can happen if your function is continuous is if you have a local maximum. It's important that one of the hypotheses of the theorem is that the function is continuous at this point. If it's not continuous, then you might get a jump, so you might not have a local maximum there. We have something similar if f prime of x changes from negative to positive. In this case, f prime starts negative and becomes positive, so f starts as decreasing and then ends up as increasing. That means we have this kind of picture here. F is decreasing, then increasing. Since our function is continuous, the only way that can happen is if you have a local minimum value there. In this third picture, the derivative doesn't change sign at c. So we have that the function is increasing and then it's still increasing. In a case like this, you have a horizontal tangent line at the point. So this critical point, f prime of c, does have zero derivative because the tangent line is horizontal, but the function is increasing on both sides. So in this case, f prime goes from positive to positive. So f goes from increasing and then it stays increasing. So in a situation like that, you won't have a local maximum or a local minimum. Let's do an example. Find the critical numbers of the function f, which is given here, and classify each critical number as belonging to either a local maximum or a local minimum, or neither. So the function is f at x equals 2x cubed minus 3x squared minus 36x plus 2. Okay, we want to determine first what the critical numbers are, and then classify them as belonging to either local maximum or local minimum values. So we start by computing the derivative. We need to know what f prime is. This is a polynomial, so we just use the power rule repeatedly. The derivative of 2x cubed is 6x squared. The derivative of negative 3x squared is negative 6x. The derivative of negative 36x is negative 36. And the derivative of a constant, 2, is 0. We can factor this. First you take out the 6, and then you'll be left with x squared minus x minus 6, which you can factor as x minus 3 times x plus 2. Thus, f prime at x is equal to 0 when x is equal to 3 and x is equal to negative 2. this derivative is continuous everywhere, so there's no place where it's undefined. So the only critical points occur when the derivative is actually equal to 0. And that happens precisely when x is equal to 3 or x is equal to -2. And that's where these two values come from. Now we make a sign chart for f prime at x. Check the sign of f prime at x for one number inside each interval. So x equals -2 and x equals 3, those are the zeros for our derivative. We just need to check the sign of the derivative on each of these three intervals that we have in our picture. Now in order to do that, you just pick any number to the left of -2, any number between -2 and 3, and any number to the right of 3. And you just plug those back into your derivative to determine if the sign of the derivative is positive or negative. Our first choice is -4. This is to the left of -2. So we've already computed it here. It's 6 times -7 times -2. We don't actually care about the value, we just care whether it's positive or negative, and this is positive. So to the left of -2, we have a positive derivative. Now between -2 and 3, we can pick 0. That's a convenient choice. And that gives us 6 times -3 times 2. Again, we just plug in 0 into the formula for our derivative. We're just trying to determine if it's positive or negative. And in this case, we end up with something which is negative. So we have a negative value there. And finally, to the right of 3, we can pick any number that we want, so for no particular reason we pick 8, just because we can. So that gives us 6 times 5 times 10, which is a positive number. And so we put a positive in our sign chart to the right of 3. You only need to check one number inside each interval, because this derivative is continuous. So the only way that it can change sign from positive to negative, or negative to positive, is by passing through 0. And we know all of the places where the derivative is equal to 0. The derivative is equal to 0 at -2 and 3. So those are the only possible places where the sign could change from positive to negative or negative to positive. If the derivative was discontinuous, then you might get a jump, and so you have to include all of the points of discontinuity as well, because you might get a change of sign at a point of discontinuity. Now in this particular case, f prime is continuous, so we don't have that. But if you have a point of discontinuity for the derivative, you need to include that in your sign chart. Okay, well now we know what the sign of the derivative is on all of these intervals, so we can determine the increasing, decreasing behavior of our function f. So if f prime is positive, then f is increasing. If f prime is negative, then f at x is decreasing. And again, if f prime is positive, then the function f is increasing. So that tells us that we're increasing until we get to x equals -2, and then we're decreasing. So we have a shape that looks like this. And then we're decreasing until we get to 3, and then we start increasing. So that means we have a shape that looks like that. So that tells us that we have a local maximum at x equals -2, and we have a local minimum at x equals -3. Let's just write that down. We have a local max at x equals -2 and a local minimum at x equals 3. Now notice here that I'm saying it happens at x equals -2 and at x equals -3. The local maximum value is what you get when you plug in x equals -2 into the function. The local minimum value is the y value that you get when you plug in the input x equals 3. So the values are the y values. The x values are the locations where you have the local maximum and local minimum values. Let's do another example. Find the critical numbers of the function f and classify each critical number as belonging to either a local maximum or a local minimum, or neither, for the function that you see here. F at x equals x squared divided by x minus 1. So, the first thing that we want to do is find the critical numbers, so that way we can classify them. We compute the derivative of f using the quotient rule. So the derivative of f is the derivative of x squared divided by x minus 1. And using the quotient rule, this is the derivative of the top times the bottom minus the top times the derivative of the bottom divided by the bottom squared. The derivative of x squared is 2x, and the derivative of x minus 1 is just 1. So if you simplify this, you end up with, in the numerator, 2x squared minus 2x minus x squared. So that simplifies to x squared minus 2x, and you can factor out an x, and you'll have x times x minus 2 in the numerator. In the denominator, you have an x minus 1 squared. We know that this derivative is equal to 0 when x is equal to 0 or x is equal to 2. These are the critical numbers for f. The derivative doesn't exist when x is equal to 1, but x equals 1 is not a critical number. That's because it's not in the domain of the function. If we just go back to our original function, in our original function we're dividing by x minus 1. That means that x equals 1 is not in the domain. So x equals 1 not in the domain. So that means it can't possibly be a critical number. However, it is important. We still have to include the vertical asymptote on the chart, on the sign chart. That's this one right here. We have to include it because the derivative might change sign from positive to negative there, or from negative to positive. It might not, but it's a possibility. So if the derivative changes sign at 1, it's not important for 1 itself. It's important because we need to know what's going on between 1 and 2 in order to compare that to what's going on to the right of 2. Well, let's just go ahead and compute these values. Well, that's already been done for us. Negative 1 is to the left of 0. So that's this first interval, this leftmost interval. And f prime at negative 1 is minus 1 times minus 3 divided by negative 2 squared. Now the numerator is positive. The denominator is always positive because it's a quantity squared. So we have a minus 1 times a minus 3 in the numerator. That's positive. So we have a positive on the first interval. Now on the second interval, from 0 to 1, we pick something, say 1/2. That's convenient. So f prime at 1/2 is a positive times a negative divided by a negative quantity squared. So the denominator is always positive. And so we end up with a negative number. And again, we don't care about what value it actually is. We just want to know if it's positive or negative. Okay, now here's the question. Does the sign of the derivative change as we go from the left of 1 to the right of 1? And if you plug in something between 1 and 2, for example, 1.5, 1.5, 3/2, however you want to say it, f prime at 3/2 is 3/2 times a negative 1/2 divided by 1/2 squared, and that's negative. So the sign doesn't change actually. Okay, now we pick something to the right of 2, like 3. We'll just pick a 3 here. So f prime of 3 is 3 times 1 divided by 2 squared, so that's positive. Okay. Now, based on this information about the derivative, we can determine when the function f is increasing or decreasing. So it goes from increasing to decreasing, and then it stays decreasing, and then it's increasing. Now, again, we didn't really care about what the sign was around 1 because you might have a local max or a local min at 1. You won't. 1 is a vertical asymptote, not just of the derivative, but the original function. You're dividing by x minus 1. So you can't have a local maximum or a local minimum at 1 anyway. But what we care about is the sign of the derivative around 2. So you can see, for example, that it's decreasing and then increasing. So it's going to have this kind of shape. Well, to the left of 1, you're going to have this kind of shape. So it's going to be increasing, then it's going to get to 0 and then start decreasing. So that tells us that we have a local maximum there. And then at 2, it's decreasing and then changes to increasing, so we're going to have a local minimum there. So let's just write this down. We have a local max at x equals 0, and we have a local min at x equals 2. This brings us to the second derivative test. The second derivative test is based on the concavity of the original function. As just sort of a hint, if we go back to our previous slide, let's take a look at this local maximum that we had at 0. Notice that the image here is concave down. If your image is concave down, then you have a little bump, and so you have a little hill with a peak. So that will correspond to a local maximum. On the other hand, this local minimum is at the base of a valley, and a valley is concave up. So if you know that you have a critical point and you want to determine if it's a peak or a valley, then it's enough to know what the concavity is there. And that's really what the second derivative test is all about. So here it is. The second derivative test. Suppose that f prime of c is equal to 0. So we're assuming that that c belongs to a critical point, and we're also assuming that f double prime is continuous at c. So in other words, you won't have any kind of jumps there. Now that's the second derivative, mind you, so we're assuming that the second derivative is continuous. Okay, so what is the statement of the theorem? If the second derivative at c is negative, then f has a local maximum at c. If the second derivative is positive at c, then f has a local minimum at c. And again, this is just looking at concavity. So let's look at A here. We have that f prime prime of c is less than 0. Well, let me just rewrite it like this. F prime prime of c is less than 0. This less than symbol, notice, sort of looks like it is concave down. And that's exactly what it means when your second derivative is negative. You're concave down. And if you're concave down, then you have a little hill, and so the peak of that hill belongs to a local maximum. And what about B? Well, for B, you have that f prime prime of c is greater than 0, or if we write it like this, f prime prime of c is greater than 0. And now if you look at that greater than symbol, that looks like a valley, which is concave up. So if you have a valley, then the base of that valley is a local minimum. So you don't need to try to memorize the theorem, just remember what concavity is. So if something is concave up, then it's going to look like this. So if you have a critical value that might be a local maximum or a local minimum, and you know that it's at the base of a valley, then it's got to be a local minimum. And if you have something which is concave down like this, then you have a little hill. So if you start out with C and you know that it's a critical point, and you know that it might be a local maximum or a local minimum, and you check the concavity there, and you see that it's concave down, then it must be a local maximum. So that's the second derivative test. So on this slide, we just repeat what I just said. If f prime prime of c is less than 0, then it's concave down. And so that means your critical number must belong. If it's concave down and you have a critical number, in other words, you have a horizontal tangent line. Let me just fix that horizontal tangent line. So if you know you have a horizontal tangent line, and you suspect that it belongs to a local maximum or a local minimum, and you discover that it's concave down there, then it must be the peak of a mountain or a hill. And so it must be a local maximum. And similarly, if the second derivative is greater than 0, so you have, remember we're assuming that your second derivative is continuous. So you're not going to have any jumps. So you know you have a horizontal tangent line there. So you want to check to see if it's a local max or a local minimum. Well, if you know that it's concave up, then it must be the base of a valley. So it must be a local minimum. Now the second derivative test fails if the second derivative is equal to 0. If f double prime is equal to 0, you can't determine concavity. The classic example is f at x equals x to the 4. So f prime of x is 4x cubed, and f double prime of x is 12x squared. In this case, there is a local minimum at x equals 0, but f double prime at 0 is equal to 0. So the second derivative is 0. That doesn't tell you anything about concavity. It basically means that the function is kind of flat there. And if your function is flat enough, then the second derivative can't tell what the concavity is. So in this picture, your graph is concave up everywhere, and you do have a local minimum at x equals 0, but your second derivative can't tell you that. So if you get that the second derivative is equal to 0, you just can't draw any conclusion. And so in a case like that, you're going to have to use the first derivative test. Let's look at an example. Well, actually, this is an example that we already looked at. F at x equals 2x cubed minus 3x squared minus 36x plus 2. This was actually our first example. We already found and classified the critical numbers using the first derivative test, but now let's do the same thing using the second derivative test. So we already found the first derivative. F prime of x is 6x squared minus 6x minus 36, which you can factor, and then you can easily read off the critical numbers as being x equals 3 and x equals negative 2. Okay, so now we compute the second derivative of f. So again, this is just a polynomial. So the derivative of 6x squared minus 6x minus 36, the derivative of 6x squared is 12x. The derivative of negative 6x is negative 6. And the derivative of this 36, that's a constant, so the derivative is 0. Okay, compute the second derivative at the critical numbers. So f double prime at 3 is 12 times 3 minus 6, which is equal to 30. So in particular, f prime prime of 3 is greater than 0. So that tells us that we're concave up, because we have our inequality is that concave up shape. So that tells us that we have a local minimum at x equals 3. Now what about f double prime at negative 2? Well, that's going to give us a negative 30. So f prime prime at negative 2 is less than 0. So that means we have a concave down shape, concave down. So that means we have a local max at x equals negative 2. Because it's concave down, you have this hill kind of shape, so the critical point must belong to a local maximum. Let's look at another example. Well, again, this is the example we already looked at, f at x equals x squared over x minus 1. And we found and classified the critical numbers using the first derivative test. And now we'll do the same thing using the second derivative test. So we know what f prime is, we computed that before, x times x minus 2 over x minus 1 quantity squared. And so you can easily read off that the first derivative is 0 when x is equal to 0 and x is equal to 2. Again, the first derivative doesn't exist when x equals 1, but that's not going to give you a critical point because x equals 1 is not in the domain. Now for the first derivative test, we actually had to care about x equals 1 because we had to check the first derivative on either side of the discontinuity. But for the second derivative test, we can completely ignore x equals 1. Now, on the other hand, we have a bit of a task because we have to compute the second derivative of f, which is a quotient. Now, the first derivative is a quotient as well, x squared minus 2x over x minus 1 quantity squared, and we now have to compute the derivative of that. But we've already got that done here. So it's the derivative of the numerator, which is 2x minus 2, times the denominator, minus the numerator, times the derivative of the denominator. So you can check that the derivative of the denominator is 2 times x minus 1, which is 2x minus 2. So the derivative of our numerator is 2x minus 2, and perhaps surprisingly, the derivative of our denominator is also 2x minus 2. Anyway, you can simplify this, and you'll end up with 2 over x minus 1 quantity cubed. So it's a little bit of work to get there, but the second derivative is quite simple. It's just 2 over x minus 1 quantity cubed. So now let's compute the second derivative at the critical numbers. So we have f double prime at 0 is 2 over 0 minus 1 quantity cubed. Well, that's just negative 2. So in particular, it's negative. F prime prime at 0 is negative, so that tells us that we have a concave down shape. So that tells us we have a local maximum. Local max at x equals 0. And for f double prime at 2, that's just equal to 2, so in particular it's positive. F prime prime at 2 is greater than 0, so we have a concave up shape, so that means we have a local minimum at x equals 2. So it's kind of a trade-off using the first derivative or the second derivative. The nice thing about the second derivative is you just have to plug in whatever your critical numbers are straight into it. Unfortunately, computing the second derivative might be a little bit more work. And the other drawback, or at least potential drawback, of using the second derivative test is that it might fail if you get that the second derivative is equal to 0. The first derivative test is perhaps a little bit more subtle, but the advantage is that it never fails.